Right, so at this point, let us reflect for a while where the natural log and the common log occurs in nature. I did a video previously on deriving the value of e, right, where e is equal to 2.718 to 3 decimal places, and we use it and we derived it from a situation where you're calculating the compound interest being earned on an investment, where the compound interest is calculated monthly, then weekly, then daily, then hourly, then every minute, then every second, and so on and so forth. And the shorter the time is, the greater the number of individual interest calculations, and the closer the value gets to 2.718, right? Now, when you have, for example, a population growth, the graph is in the form of y equal a number times e raised to the power of x, where you have the y-axis here and the x-axis here. So you do have e there. If it is a case that you have decay, for example, you have a pot that was boiling, a pot of water was boiling, you turn the stove off and say every 1 minute you take the temperature of the water. It will cool over time, right? And if it started at say 100 degrees Celsius and after 1 minute it cooled down to 90 something degrees Celsius, after 2 minutes it cooled to 80 something or whatever it is, still 90 something, and you take it every 1 minute, right? At some point you plot the graph of temperature, the y would be temperature versus time, the x would be time, all right? You will find that y equals a number e raised to the power of negative x, all right? So in this case, what you have is a cooling. Let me use my graph plotter and see an example of what the graph might look like. All right, waiting for my graph plotter to load up. Oh, it's my graph plotter that I wanted. So let me wait until it loads. GeoGebra. All right, so if you have a graph here, I like to see the grid on the graph. So let me do that. Nice. If you have a graph here that says y equal e, which is 2.718, the 3 decimal places, raised to the power of x, you have that, which is like a population growth or some other exponential growth. Let me make my line very thick. Nice. And I have y equals x. Let me adjust it to y equals a number times e to the negative x. And what you have is a decay, alright? Like cooling. It could be y equal 4 times e to the xy equals 6 times e to the x, whatever number, times e to the x, or t to the e to the negative x. Alright, the pot will be cooling at this time, at this point. Let me add 1 to it to raise the graph a bit. Alright, so over time it will cool and cool and cool, and after maybe 2-3 hours, or it could be even more, it will cool to the point where if you are in a room that is at 30 degrees Celsius, say the room is 30 degrees Celsius, the water will cool down to the point where it gets close to or reaches 30. In real life it would reach 30, but it will never get cooler than 30, right? Unless you put some cubes of ice in it and stir it, but it's not going to get colder than the surrounding air temperature. Alright, so this is an exponential decay. In nature, it follows a number times e, whatever that number is, right? It will follow a number, say call it a, times e to the negative x. Alright, so that's what would happen. Now, as for common logarithms, in that case, they use, for example, the decibel scale used to measure the intensity of sound, and the Richter scale used to measure the intensity of earthquakes. You have, for example, an earthquake measuring as a magnitude of 0 on the Richter scale. Well, there is no shaking. And you have an earthquake with a magnitude of 1, another with a magnitude of 2, a magnitude 3, magnitude 4, magnitude 5, magnitude 6, and so on the Richter scale. Now, it is said that a magnitude 2 earthquake has 10 times, call it 10x, the amount of energy as a magnitude 1. A magnitude 3 has 10 times the energy of a magnitude 2. And therefore, the magnitude 3 would have 100 times the energy of a magnitude 1. And so on. Magnitude 6 earthquake has 10 times the energy of a magnitude 5. And so on. Remember, when we find logarithms and we say the logarithm of, let me clear it, log 10 is 1, log 100, log 100 is 2, log 1000 is 3, and so on and so forth. So log 1 is 0, log 10 is 1, log, let me write it going upwards like this scale that we have here. Log 1, we cannot have a log 0. Log 1 is 0, log 2, log 10 is 1, log 100 is 2, log 1000 is 3, log 10,000 is 4, and so on and so forth. What we're looking at is the logarithms. So when you look at the Richter scale, notice that the answer with a magnitude 3 is 10 times larger than the answer with a magnitude 2. because the log of the number that you're looking at, when you look at a number, you see that 1000 is 10 times larger than 100. And here, with the 4, the answer with a magnitude 4 has 10 times the value of a magnitude 3. In other words, 10,000 has 10 times the value of 1000, right? So that's how they set up the Richter scale, all right? That's how they set it up. All right, so those are where you find logarithms, both common logarithms and natural logarithms, being used, occurring and being used in real life. All right, so we'll continue looking at logs and exponents in later videos. So I'll see you then.